Thanks so much. Good to be back here. The last one was Annex 81, and that one is finished, and so therefore I was able to present you lots of results of things that we've done, whereas Annex 96 has just started. So this is the gonna do presentation. That is what we're going to do. Did you know that buildings have got stuff down in the basement that can shift the time of day in which they actually use their energy? That could be electric batteries, it could be thermal batteries in the form of hot water or air conditioning. It could be transport batteries in the form of electric vehicles. All these things can charge up earlier in the day, discharge later in the day, and vice versa. And provide that flexibility, the ability to shift load around. But those loads are generally not grid connected. That is pretty much invisible to the electricity system. So what we need is to bring the two together so that when the renewable energy is powering away, we can use that energy, and when it's not, we can back off on our energy consumption. Is that a good idea? Well, this is a graph of the electricity system on a spring day in my state of South Australia, and it shows the different sources of energy in the electricity system between midnight and midnight on a spring day. The yellow there, the lime yellow, is rooftop solar PV, so over a third of Australian houses have got solar sitting on the roof. And the green is wind, and the orange is gas-fired generation, and the purple there is imports from the neighbouring state. What you see is on that spring day, our entire electricity system is running on rooftop solar PV, and indeed there is so much renewable energy available that it has to be pushed off to other places around Australia. So if you've got this source of low emissions electricity in the middle of the day, and there's so much of it that prices in the wholesale market actually go negative. So it's effectively free and it's low emissions. You can have your cake and eat it by consuming this kind of stuff. Conversely, in the shoulder periods, the sun's gone down, there's not much renewables in the industry, you've got fossil fuels that are driving the electricity system, and that costs money to run, and so that is, if you like, the expensive energy in the system. So what we're trying to do here is get our buildings and anyone that has these flexible loads to actually shift their load out of the high-price fossil fuel energy time and into the low-cost, low-emissions time of day. Is that a good thing to do? Well, the International Energy Agency thinks that that's a good thing to do, and I showed you this slide, or a slightly different version of it, but showing that the net zero by 2050 has got targets there for managing our demand to coincide with renewables. So it's not just an environmental sustainability thing, but also it actually is good for the reliability of our grid. We're transitioning the entire system. We're finding, in many jurisdictions, things like coal-fired power is coming to the end of its life, and it's being phased out and being replaced with renewables. And at the same time, we're electrifying all our energy consumption in buildings, and that's actually increasing the amount of supply actually required. So generation being taken offline just as we're trying to put more stuff onto the electricity grid, that seems rather tricky. So can this flexibility actually do a good job? Well, here in this one in the New York ISO there, it's a grid that has got 37.7 gigawatts of generation servicing it. And of that, 1.7 gigawatts is imports and 1.5 gigawatts is from demand response, up 16% in 2025. So that 1.5 gigawatts out of 37.7 may not sound a lot, but that's a hell of a lot when it comes to dealing with those critical moments in the system. So that's genuinely meaningful stuff that we can contribute. All right, a little bit more context, because I haven't got so many results to provide. I can give you lots of context. If you're paying your bills, what you do is you've got someone who says, I'll have, is it 30 cents a kilowatt hour or whatever the number is, and then that money gets divvied up into all these things on the electricity industry side of the equation. Account management, wholesale energy, balancing, emergency, networks, that's the poles and wires, and environmental. It's a one-way flow of dollars to all these services that are being provided to give you electricity. But new world here is that we're actually sitting there with our electric vehicles, our batteries, our hot water systems, our HVAC that's flexible. We're actually reversing the idea of the service. That is, ideally, we as buildings, using our flexibility, are providing a service to the electricity industry. And so the big question, unresolved question I would say, is how much should that flexibility be paid, and what firmness does it offer when it's asked for? Is it real or is it not? So those are kind of the challenges that, that this annex is trying to address. How do you go about establishing value for this resource called flexibility? Here's another context slide here. I haven't connected all the dots yet, but it just shows I'm sitting there, I'm a customer, I'm saying, whoa, what's going on here? Do I look to my retailer just to give me a better deal on my electricity? And I would say, philosophically, if you're looking downwards as the customer towards the green side of this plot, you're a customer as an energy buyer, and you're looking at tariff structures as the way you go about purchasing. And what you're then trying to do is you get given this tariff structure and you try to use your flexibility to avoid consuming energy at high price times. So you're continuously shifting your load around in some way. Problem with that is all of the costs that are bundled up into those tariffs, they've all been smeared across the entire year, and they've been smeared geographically so that we all receive sort of one and the same kind of tariff. And the problem with that is there's not much of a price signal to provide any service. Alternatively, the customer could look up and say, well, actually, if you need my stuff, I'm going to be a participant in your electricity system. And every time you call on me, I'm going to actually do something for you, and I want to be paid, and I want to be paid quite handsomely. Thank you very much. And so in that case, rather than being penalised for the energy you consume through your tariff, that's the looking down, instead you're actually getting paid to provide a service. Problem there, of course, is complexity. I don't know, there's too many people that actually want to fully understand the nuance of electricity systems, and so there may need to be a fair bit of hand-holding there. But they're two quite fundamentally different ways of looking at. One's an implicit price-responsive approach, that's the downward-looking. One's an explicit event-based. When you call on me, I will offer my flexibility. Interestingly enough, it also works, and I've sort of got separated to the left and to the right. There's a real-time problem. Can I actually respond in seconds for balancing, or minutes or hours or day ahead, things like that? And so that's around the OPEX, cost recovery. And then there's a big planning dimension. How many power stations do I need to build, or how many poles and wires do I have to put down the street with or without these buildings providing their flexibility? That's your 101 of the electricity industry. I hope you enjoyed that. Let me go now to Annex 96. So, what's Annex 96 trying to do? It's trying to unlock the potential for these flexible assets that I have mentioned. And we want to do it for two reasons. We want to help with the clean energy transition of the electricity industry, and we also want to do it because we want to consume energy when the renewables are there. That's the low emissions part. So it's both an electricity security and also an emissions story. And in terms of the aims then of what we're going to do, we're going to go and look at it at a building level and all the different flexibility technologies. We're going to try and improve their technology readiness level, make them more a firm resource. We're going to look at the measurement and verification. That is, how do you even know whether you provided flexibility? Can we measure it in some way? As many of you will probably know, it's actually quite difficult to measure an absence of electricity consumption. And so there's a whole range of technical difficulties there. And we want to use digital machine learning technologies and the like to also be able to forecast in advance how much flexibility we have at any given moment. One of the barriers also is around interoperability. That's our technologies that don't talk to each other. They've perhaps got proprietary communications protocols, and we need to standardise on the language and key performance indicators that we're using to present our information. Because typically flexibility is not a drop-in replacement for existing supply-side systems, so we have to create our own nomenclature to some extent. There's a bunch of different issues when we start playing with our loads. Potentially we switch them off to respond to a high price signal, then the high price signal goes away and we then turn them back on, and suddenly there's this rush of demand that happens. So rebound effects are an issue. So looking at the coordination of lots of assets is also a key thing that we're doing. And lastly, an idea of time of use emissions. Rather than using average annual emissions factors, can we use localised hourly emissions factors? I showed you that plot of the renewable energy in the middle of the day. Clearly in the middle of the day in South Australia in spring, the middle of the day the emissions is zero. Whereas if I go into the later on in the day, then there is high emissions. So these are the things that we're looking at. We're structured for subtasks, as is traditional. Subtask A, grid scenarios and interoperability, is really looking at those communications issues to get that common language, similar to the metadata schemas that I was talking about this morning. Subtask B, flexible demand aggregation, is particularly focused on that aggregation. What happens when we've got lots of coordinated loads, perhaps in what's called virtual power plants, and how are they good or bad for the grid? Then subtask C is drilling into the individual components inside the building. That's the HVAC, the hot water, and electric vehicles and other loads. And finally, subtask D is case studies and implementation. And ideally, we'll end up with a roadmap providing advice on how to grow this industry, similar to 81. We've got a lovely crew of enthusiastic and competent subtask leaders spanning across both North America, Europe and Asia Pacific, and representing both industry and academia. And here's our superpower, which is our participants. We've got more than 60 organisations across 20 odd countries. And one of the fun things that we do is we have PhD forums each meeting, so it's twice a year. And Media, a air conditioning company, is the sponsor of the PhD Forum Prize for presentations. So there's a couple of our winners over the last two meetings down there on the bottom. All right, so we've got this new thing that we do in our annexes is we create a theory of change. How would it be that we do a bunch of stuff and someone might take it up and do something useful. So we've got to define our problem and then show how we're going to solve that problem. So there I've got 5 problems, and I've pretty much run through them already. One is around awareness. Do people even know about this thing called flexibility? Perhaps we need some kind of educational work around that. Measurement and verification, I talked about. How do we pay people for this thing called flexibility? It's obviously got to be based upon measuring something. The interoperability issue, information and data need to be collected to be able to do anything. That rebound effect thing that I was talking about is talks to the way the electricity industry treats sources relative to the way generation relative to load. Generation, they want to know everything about every single device, whereas on the load side, we take it statistically. And so we're trying to bring this sort of statistical perspective to it to say, on average, our load will be able to provide this much flexibility and have sufficient confidence levels to be able to run the grid. And then the fact that all our policy makers all use annual average emissions at the moment. Clearly, we've got to convince them that hourly emissions is a more appropriate metric going forward as we go through the clean energy transition. So we've got a bunch of inputs. As I said, our superpower of our lovely researchers, amongst other things. We've got a series of outputs. I won't go through each of them on a blow-by-blow basis. And then how that tracks through to, if you like, the grail at the bottom of emissions reduced, lights stay on, and energy cost is down. So here's just one of those theories of change. This relates to the measurement and verification. Luckily, we've got a bunch of researchers and industry out there that have been developing measurement and verification algorithms for quite a while. So we're collating those and validating them as appropriate for paying, for measuring flexibility such that people can get paid. Nothing like people getting paid to lubricate some action. And a related task that activity that we've done already, even though we're only 6 months in, is we ran an AI competition called the Flex Track Challenge. This is where we offered data to people. The data consisted of the load profile of various buildings. We gave them ground truth data as to when we were switching on flexibility, and we gave them ground truth data of how much flexibility we said that they actually delivered. And then we gave them blind data and said, tell us how many times we activated flexibility and tell us how much we delivered. And so ran it on AI Crowd. We had a number of teams. Indeed, we had 92 teams from 50 countries submitting their solutions. And India, congratulations, you had the most participants, 60 participants, and indeed you're well represented on the leadership board there. And it was 10,000 Australian dollars, $20,000 of Australian dollars of prize money, of which 10,000 was prize and 10,000 was travel money. And so a bunch of lucky people, hard-working, competent expertise people getting a free trip to Wollongong in December to receive their prize. Here's another theory of change. This one relates to the interoperability thing. And we're scouring the world for test labs to help test equipment to the extent that they are able to talk to each other. And so we've identified 3 labs there where we'll be doing putting batteries and other heat pumps and other devices under test to work out whether they can talk to each other. Here's another one, which is around, as I said, that rather arcane idea of stochastic measurement of and forecasting of building loads. Luckily here, amongst our wonderful team members, is we have 3 virtual test environments. And so what we're going to do is simulation-based scenario analysis to work out whether flexibility can actually do the job, who gets the money, and whether the lights stay on. And what we're asking people to do in these common exercises using these test beds is bring their control strategy or flexibility orchestration strategies together. In Annex 82, we kind of categorised 4 different types of control strategies. One type is the centralised. That's the one with the all-knowing brain that knows every single asset and individually polls them and controls them. That's the big brother one. That's number A. Number D, the non-hierarchical distributed, is kind of the agent-based approach. That's where all of these flexibility things, they're just talking to each other, just communicating like we're communicating, and they're just learning what to do and coordinating themselves rather organically. And then we have a couple of hybrids, that's B and D, decentralised and hierarchical. So we want researchers to bring their methodology to our AI gymnasium and test out which of these control strategies does the best job of coordinating large numbers of buildings. So standard buildings, everyone gets the same buildings, everyone gets the same grid, but they bring their controller and there's a set of KPIs or rewards for success. Last one, then, this is again around the time of use-based emissions rather than annual emissions. We've got a bunch of researchers very interested in this. It's a relatively new area because we're in such a transition in the buildings industry, and they're going to collect data on time of use emissions factors and look at whether it really makes a difference. Is it a 10%, is it a 20%, is it a 50% difference? I did a thought experiment with some of my colleagues there, and this is the framing of the problem, okay? So the red line that you see there is the load of the building, the demand for electricity, and the blue line is the generation of solar PV on site. And so this problem is framed around, I'm going to get all my renewables from on site, and I want to call myself a net zero building. So to be able to be net zero, what I want is the pink, that's the solar generated, to be more than the demand and export that into grid to offset the consumption on the shoulder periods, that's the yellow stuff. So if pink balances the yellow, I'm net zero is my claim. Seems like a logical kind of a thing. Problem is that right during that window, your grid is probably at zero emissions as well, because everyone else has got solar at exactly the same time. And so it's pretty artificial to count that pink stuff as being useful at all. So we ran through a bunch of 4 different buildings that we had a lot of data on. We put different climate zones, that's Queensland, New South Wales, Victoria, Tasmania and South Australia, and said, if we gave you no value for that pink stuff, and you want to call yourself a net zero building, how much is your emissions really? And it works out that you've only probably gone about 50% emissions reduction. You're not zero emissions at all. Yes, you may call yourself net zero, but you're about 50% of what you would have been otherwise. So I think there's lots to tease out in that. It's a vignette, but over the course of the annex, I hope to come back to the Exco with, hey, this is a real thing. We need to do something about it and do something quick or not. So I'll finish up there. I hope that's interesting. Similar to Philip, we've just got started, so you're certainly most welcome to contact me and join Annex 96.
So we do have time for one question from the audience. So
for the emission factors, how do you propose to estimate them?
I think many jurisdictions actually publish which power stations are running and their emissions. So certainly in Australia, and we have with CSIRO, we've done flow tracking of this power station was dispatched, etc. So we've got a historic basis, and the more recent research then is to say, can we have a 72-hour ahead forecast of emissions? That gets a bit more tricky, just trying to predict what it's going to be in future. And we want to do that because we'd love to do model predictive control based on future emissions rather than on price.
You're lucky.